When sizing electrical panels, especially for loads like rooftop units or RTU, it's crucial to understand the concept of continuous versus non-continuous loads. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. Non-continuous loads, on the other hand, are loads that do not operate at their maximum capacity for extended periods. This distinction is vital because the National Electrical Code, or NEC, provides different guidelines for sizing panels based on the load type. In the specific case of adding 4 RTU, each with a full load amperage, or FLA, or 49.8 amps and a minimum circuit ampacity, or MOC, of 90 amps, and planning to supply them from a new panel, it is necessary to determine if the engineer's proposal of a 200 amp panel with 4 90 amp breakers is adequate, or if a larger 400 amp panel is needed. The engineer's argument rests on the assumption that the RTU represent a non-continuous load, meaning they won't all operate to their maximum capacity simultaneously. This is a common scenario for cooling loads, as peak demand usually occurs during specific hours and not consistently across all units. The NEC mandates that electrical panels be appropriately sized to handle the expected load. For continuous loads, the panel must be sized to accommodate 125% of the continuous load plus 100% of the non-continuous load. However, for non-continuous loads, the NEC permits a reduction in panel size, recognizing that the full load will not be sustained continuously. Article 408.54 of the NEC provides guidance on sizing panels for non-continuous loads. It allows for a calculation that incorporates a diversity factor, which accounts for the fact that not all units will operate at their full capacity concurrently. The formula for calculating the panel size for non-continuous loads is the sum of individual unit loads multiplied by the diversity factor. The diversity factor is a multiplier, typically less than 1, that represents the probability of all units operating at full load simultaneously. This factor depends on the type of load, the application, and historical data. For cooling loads, a diversity factor of 0.7 is often considered typical, but it can vary based on the specific application and climate conditions. Now let's apply this to the given scenario. The total load for the 4 RTU is calculated by multiplying the individual unit load, 49.8 amps, by the number of units, which is 4. This results in a total load of 199.2 amps. Then, assuming a diversity factor of 0.7, the required panel size can be calculated. The panel size equals 199.2 amps multiplied by 0.7, which equals 139.44 amps. This result suggests that a panel size of approximately 140 amps would be sufficient to handle the non-continuous load of a 4 RTU. Given the standard panel sizes are available in increments of 100, 125, 150, 200, 225, and so on, a 200 amp panel would be the next available size above the calculated 139.44 amps. Therefore, the engineer's proposal to use a 200 amp panel is technically correct based on the assumption of a 0.7 diversity factor. However, there are several important considerations to keep in mind. Firstly, it's essential to verify the appropriateness of the 0.7 diversity factor for the specific application and climate. A higher diversity factor may be necessary if the RTU are expected to operate closer to their full capacity for extended periods. Secondly, it's crucial to consider future expansion or additional loads that may be added to the panel in the future. Sizing the panel too close to the current load may limit the ability to add additional equipment without upgrading the panel. Thirdly, it is necessary to consider the conductor ampacity when selecting the correct overcurrent protection for the conductor size. NEC Table 310.16 details the allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius to 90 degrees Celsius. If the conductors that feed the panel are rated for a higher amperage and the conductors that feed the RTU are of the correct size, then the breakers will trip before the conductors are overloaded. Next, consider the minimum circuit ampacity. While each RTU draws 49.8 amps at full load, the minimum overcurrent protection is required to be 90 amps. This suggests a transformer in the RTU itself needs 90 amps to handle its own inrush current. With 4 90-amp breakers for each RTU, the total amount of amperage the engineer has proposed on this panel is 360 amps. When installing the 4 90-amp breakers on the 200-amp panel, it's important to understand the 80% rule. This rule, described in NEC section 384.13, states that the load on any overcurrent device located in a panel board shall not exceed 80% of its rating, where in normal operation the load will continue for 3 hours or more. It is required for continuous loads. This ensures that the panel and its components are not overloaded, which can lead to overheating and potential safety hazards. In summary, while the engineer's proposal to use a 200-amp panel for the 4 RTU is technically correct based on the non-continuous nature of the load and a diversity factor of 0.7, it is essential to verify the diversity factors appropriateness, consider future expansion, and ensure compliance with the 80% rule. A more conservative approach, such as using a 225-amp or 250-amp panel, may provide additional safety margin and allow for future expansion. Ultimately, the decision on the appropriate panel size should be made in consultation with a qualified electrical engineer, taking into account all relevant factors and applicable codes. The engineer must evaluate the specific conditions of the installation, including the climate, the building's occupancy, and the expected usage patterns of the RTU. This information should inform the selection of an appropriate diversity factor and ensure that the panel is adequately sized to meet the demands of the connected loads. Remember, safety and compliance with electrical code should always be the top priorities when sizing electrical panels. The engineer's calculation needs to adhere to NEC Article 220, which provides requirements for calculating branch circuit, feeder, and service loads. Following these guidelines ensures that the electrical system is safe, reliable, and capable of handling the anticipated load. It's important to note that local codes and regulations may have additional requirements or restrictions that must be followed. Always consult with local authorities and qualified professionals to ensure compliance with all applicable codes and regulations. In addition to the above, there are several other factors that should be considered when sizing electrical panels. These include the voltage drop, the available fault current, and the coordination of overcurrent protective devices. Voltage drop refers to the decrease in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for limiting voltage drop to acceptable levels. Available fault current refers to the amount of current that would flow in the event of a short circuit or ground fault. Electrical panels and other electrical equipment must be rated to withstand the available fault current at their location. The coordination of overcurrent protective devices, such as circuit breakers and fuses, is essential for ensuring that the electrical system is protected from overloads and short circuits. Overcurrent protective devices should be selected and coordinated so that they trip in a manner that minimizes the extent of the outage. Finally, it is important to keep accurate records of all electrical work that is performed. These records should include the panel size, the size and type of conductors, the size and type of overcurrent protective devices, and any other relevant information. These records can be helpful for troubleshooting problems and for making future modifications to the electrical system. In conclusion, sizing electrical panels is a complex task that requires careful consideration of a variety of factors. By following the guidelines in the NEC and consulting with qualified professionals, it is possible to ensure that the electrical system is safe, reliable, and capable of handling the anticipated load. Non-continuous loads offer an opportunity to reduce the panel size based on the diversity factor. A lower diversity factor is a good sign and can help save money on the electrical panel. Using the diversity factor to reduce the wire size may not be a good idea unless there is an acceptable reason for it. Remember, the calculation that was performed earlier was 199.2 amps multiplied by 0.7, which equals 139.44 amps. This is the key to saving money on the electrical panel. If the diversity factor was 1, then the calculation would have been 199.2 amps multiplied by 1, which equals 199.2 amps. This means that a 200 amp electrical panel is cutting it close. It might be worth upsizing to a 225 amp or 250 amp panel to provide a buffer for future expansion or increased load. The engineer's proposal should be carefully evaluated. Another consideration is ambient temperature. If the panel is located in an area with high ambient temperatures, the ampacity of the conductors may need to be derated. This means that the conductors will be able to carry less current than their rated ampacity. NEC Table 310.15 details the correction factors and ambient temperatures. This is important to consider when determining the appropriate size of the conductors and overcurrent protective devices. The calculation presented considered the total load for the 4 RTU, calculated by multiplying the individual unit load 49.8 amps by the number of units, which is 4, resulting in a total load of 199.2 amps. The 90 amp MOC is very important to consider. The engineer stated that he wants to use 4 90 amp breakers on the 200 amp panel. This will cause the panel to be overloaded and go against the 80% rule. The panel can supply up to 160 amps for continuous use and 200 amps for non-continuous use. With all 4 breakers on, the panel could trip or cause a potential fire hazard if there is too much current flowing through it. It is necessary to select a panel size that will be able to handle the load of all 4 RTU and any other loads that may be connected to the panel. It is also important to consider the voltage drop and fault current when selecting a panel size. NEC Article 215.2 details the feeder conductor ampacity, which should not be less than 125% of the continuous loads, plus 100% of the non-continuous loads. The goal is to choose the correctly sized conductors and overcurrent protection.